Hello, I'm Chu Chen. I'll present Visual-Inertial-Aided online MAV system identification. The state estimation and online system parameter ID are crucial for MAV. First, many control tasks require accurate system parameters. Also, platform reconfigurations makes the online system ID even more important. This is difficult because the high dynamic motions and under-accuracy can challenge the online state estimation. As a resource-constrained platform, it also requires the estimator to be lightweight and efficient. In this work, after a thorough investigation, we show that naively fused MAV dynamic might hurt performance because of the model inaccuracy. We develop a novel Schmidt kalman-filter-based visual inertial estimator, prevent navigation performance, and accurately and robustly recover system parameters online. The system is evaluated with both simulations and real-world experiments. The platform includes the global, body, IMU, camera, center of mass, and rotor frame. Given the rotor speed measurement RMI as input, which is corrupted by the noise NRI, the single force and moment can be derived, and the single force acts along the local z direction. CT and CM are thrust and moment coefficients we want to calibrate. We can then calculate the total force and moment. The MAV dynamic model can be defined with its rotation, position, angular, and linear velocity. In summary, the system parameter state X data has the thrust and moment coefficient, mass, moment of inertia, translation between the body and the MAV, and IMU to MAV extrinsics. This dynamic model is well known and commonly used in many control tasks, but it's a simplified model and is not perfect. As we only model the force along the local z direction, it cannot represent the true force when the joint rotating. This will further challenging the online parameter ID. The video shows one of our simulation trajectories, and the figure shows the difference between the model calculated force and the true force, which has arrows along the x and y directions. To compensate for this, besides the rotor speed measurement noise, we also add the system modeling noises NF and NM. The goal of the system is to perform online MAV visual inertial navigation and system parameter ID. Given the imperfect MAV dynamic model, we want to efficiently and accurately recover its parameters. Our filter-based visual inertial solution can perform both state estimation and MAV parameter identification. The system state includes the active VIO state, XA, the parameter state, X data. The VIO state includes the IMU, the feature, and clones. Since we want to build a connection between the IMU and MAV dynamics, we clone not only the IMU pose, but also its angular and linear velocity. From a high level, there are three sources of measurements. We first use the IMU to propagate state forward. The visual measurements are processed with the standard MSCKF update. Finally, the MAV dynamics can also update the filter. We now introduce how we formulate the MAV dynamic measurements. As before, we can integrate MAV state, use the dynamic model, summarized as GM. Second, we connect the MAV and IMU, use their rigid body transformation, denoted as HT. Finally, we get the linearized measurement equation, which is a function of the active state, parameter state, and measurement noises. A natural question here will be, why do we propagate the state using IMU dynamics instead of the MAV dynamics? Compared to MAV dynamics, IMU can fully capture the 6-stop trajectory evolution. This can also allow us to perform outlier gating tests to reject invalid measurements and ensure system consistency. After we get the linearized measurement equation, we can perform standard EKF update. It will update the mean of both states and their full covariance. Our numerical analysis already show the dynamic model is inaccurate. As expected, the MAV modeling noises are very crucial. Overconfident noises will hurt performance. To address this issue, we propose the Schmidt kalman filter. The key idea of SKF is to not update VL state and its marginal covariance. As the result shows, it protects VLO navigation performance no matter what noise we are using. But the visual measurements are still processed with standard EKF. As the cross correlations are properly tracked, this will refine parameters and get accurate calibration results. Our simulator is built on OpenVINS. We use rotor S to generate the joint trajectories. The parameters in the simulator are listed in the table. The simulation shows the system parameters can quickly converge. We also evaluate the system on real-world Blackbird dataset. As expected, SKF has the same performance as OpenVINS. The EKF-based estimator can work after noise parameter tuning. But when the motion is dynamic, the EKF hurt VLO, because the MAV dynamic model will be even worse under high dynamic conditions. The SKF formulation is more robust and ensures accurate parameter identification. Finally, the system parameters can converge quickly. In conclusion, we investigate the accuracy of MAV dynamic model and show naively fusing MAV dynamics can hurt VLO performance with overconfident modeling. The SKF formulation protects VLO performance and ensures safe, robust, and accurate online parameter ID. The system has been evaluated with both simulations and real-world experiments. As an extension, it will be interesting to integrate and evaluate the estimator with fully autonomous system. The generate motion analysis and observability-aware motion planning will also be interesting directions. Thank you.